If we continue to talk about the chemiosmosis part, we take a closer look at this ATP synthase enzyme and how it's actually going to function. The ATP synthase enzyme is going to utilize the energy in a hydrogen ion gradient. In this diagram, we're seeing the ATP synthase enzyme in a different orientation than what it was on the slide, but the top part of this would represent the matrix area of the mitochondria, and the bottom part of this is going to represent the intermembrane space. So down here on the bottom would be where we have the high hydrogen concentration, and this means that the hydrogens are going to want to flow up in this slide through the red tunnel that we see, and as they flow up, it will cause this wheel to turn, which will also cause this to turn. So if we take a look at that, notice the hydrogens are flowing through. They are flowing through by the process of facilitated diffusion. They're going high to low. And as they go high to low, we see that this wheel turns, and we also see the ADP and the phosphate coming in and being joined together. Now, at first it doesn't look like there's much happening up here in the top of this enzyme, but this next animation is going to take essentially a cross section right through here so that we can get a better look at what's happening inside. What we see on here, this would be the rod that we saw turning before. This is the part, the red part, that looked to not have anything much happening in it before. But this enzyme has 3 subunits that do essentially the same thing. Each one of them can accommodate 2 substrates. They can bind ADP and they can also bind phosphate. As that rod turns in the middle, it's going to cause this active site to change shapes so that it forces the ADP and the phosphate together. So if we look at that, this is showing you how we're actually going to make our ATP or put our ATPs together. So this whole process is going to be what we call chemiosmosis. In chemiosmosis, we are taking the energy stored in a hydrogen ion gradient, and we're using that to put the ATPs together. Specifically, an ATP synthase enzyme will be involved, but that's going to provide a tunnel that these hydrogens can flow through, and that will cause the wheel to spin, and it will change the shape of this active site. So if we go back to our slides, here are just the links for those animations if you do have a desire to go back and look at them again. But chemiosmosis is this process in which energy stored in the form of a hydrogen ion gradient across a membrane is used to drive cellular work. Keep in mind where that gradient came from. That gradient was generated by the electron transport chain as the energy was being released from those electrons. Want to point out that this gradient is sometimes referred to as a proton motive force. Hydrogen ions are very often called protons because essentially that is all that makes them up. So do know that a proton motive force is the same thing as a hydrogen ion gradient. There is energy stored in that gradient. If we look at the whole process of oxidative phosphorylation, we had 2 halves to it. We had the electron transport chain part. That assembly line is embedded in the inner membrane of the mitochondria, and we will have NADH and FADH2, which gathered electrons. Previously, they're going to bring them to the electron transport chain. As they pass those electrons in, they will become oxidized, which means that they can return to the electron transport chain and gather more electrons. As the electron transport chain passes the electrons along, hydrogen ions will be picked up from the matrix and they will be transported into the intermembrane space of the mitochondria. So this would be the matrix down here. This will be the space up here in this diagram. At the very end of the chain, the oxygen gas is going to gather those electrons and turn into water. Now notice here that the NADH is going to pass its electrons in at the very beginning of the electron transport chain, but the FADH2 will not pass them in until what we call complex 2. This means that when the FADH2 passes the electrons in, we will not get as many hydrogens moved across the membrane as we did with the electrons in NADH. This makes the FADH a little less valuable than NADH. Once we have this high hydrogen concentration, those hydrogens are going to flow back through the ATP synthase into the matrix, and we get our ATP put together by chemiosmosis. Notice how we are cycling the electrons around. Cycling the hydrogen ions around. We will move them across the membrane, they will flow back through, and then we will move them across and they will flow back through. They will quit flowing through the ATP synthase when we get to equilibrium. So that means that we want to continually run the electron transport chain so we do not get to equilibrium. If we talk numbers, the NADHs will move enough hydrogens across the membrane to power enough turning of the ATP synthase for 3 ATPs. The FADH2 will not move as many hydrogens across. For those, we only get 2 ATPs each. If you think about the numbers we had before, we had 10 NADHs that we were working with. So those 10 NADHs will be multiplied by 3 ATPs each to give us 30. And then we've got 2 of our FADH2s, and those are going to be multiplied by 2 ATPs each, and that's going to yield 4. So that gives us our other 34 ATPs, which we said was going to be about 90% of our ATPs that we're going to get in cellular respiration. So the overall process of cellular respiration is to take energy stored in organic molecules, release that energy in a controlled fashion so that we can make some ATP with it. This is showing us what happens to the energy. Initially, the energy was in glucose. We collect the energetic parts, which were the high energy electrons. We make some NADH. We pass the electrons to the electron transport chain, which converts that energy into a proton motive force or a hydrogen ion gradient, and then that energy is used to make some ATP. Overall, 40% of the energy stored in the glucose will get transferred to the ATP. So we want to understand how efficient it is. We also want to understand that 60% of the energy is not getting packed away in the ATP. If we look at a nice summary slide of all of this that shows where our yields come from, this slide shows us not only our yields, but it also shows us where in the cell we're getting these. If we look at glycolysis made 2 ATPs. These were by substrate level phosphorylation. They were out there in the cytoplasm and they're ready to be utilized right away. Additionally, it made 2 NADHs, so we're holding on to high energy electrons out here. For those electrons to be used in the electron transport chain, they must be transported to the electron transport chain. Because the NADH is a large molecule, we will not pass it across the membrane because that would be rather complicated. So instead, we're going to pass just the electrons across the membrane. When those electrons are passed across, the molecule that grabs them on the other side varies a little bit depending on cell type. So sometimes when they're passed across, they will be grabbed by NAD pluses and turned into NADHs on the other side. Sometimes they are grabbed by FADH2s on the other side. So those NADHs will turn into 2 NADHs in the matrix or 2 FADH2s in the matrix, one or the other. That will ultimately affect our final yield because we said that NADHs pass in at the beginning of the electron transport chain and generate more hydrogen ion gradient than the FADH2s do. We take the 2 pyruvates, and if we ship them into the mitochondria, they will get converted into 2 acetyl-CoAs. In the process, they will make 2 NADHs. We go around the citric acid cycle. It spins twice per glucose. We get another 2 ATPs by substrate level phosphorylation, and we get 6 NADHs and 2 FADH2s. When we run the oxidative phosphorylation, it comes back to all of these electron carriers. And by electron carriers, we mean NADHs and FADH2s. Those are going to take those electrons to the electron transport chain, pass them in so that we get the hydrogen ion gradient and so that we get the ATP made. If we get these from the cytoplasm passed in as NADHs, we end up with 2, 4, 10 NADHs, which gives us 30 ATPs, plus another, ignore that, plus another 2 times 2, another 4 ATPs. That gives us our 34 number of ATPs. These are ATPs made by chemiosmosis. We want to understand that yes, we do get up to 38 ATPs per glucose, but we also want to realize that 4 of them are made by substrate level phosphorylation and 34 of them are made by chemiosmosis. If you are asked how many are made by chemiosmosis or which ones are made by chemiosmosis, we need to realize that the NADHs and the FADH2s are the ones that contribute to that, because the chemiosmosis comes from the hydrogen ion gradient, which comes from the electrons. So it's all about the electrons when we talk about the chemiosmosis part of it. Now this slide is useful when we are looking at yields. We've talked a bit about yields of ATP per glucose that we get. We could also consider yields starting with other materials. So if, for example, we had a bunch of pyruvate inside the cell, we could certainly take the pyruvates and start breaking it down. If we did that, we would start with pyruvate. So that means anything that happened before the pyruvate would be stuff that we ignore. So if we take 2 pyruvates and we say, what is the yield per pyruvate? We'd take the pyruvates, ship them in. We would get 2 NADHs. So if I just write those right there, so we got those. We're going to take our 2 acetyl-CoAs that we get, spin them around the cycle twice. We'll get our 2 ATPs. We'll get these 6 NADHs. And we'll also get 2 FADH2s right here. Then if we want to know the total ATP amount, we take these and multiply them by 3. What's the 3? Times 3 and times 2 for our FADH2s. So we end up with 6 and 2 and 18 and another 4. Okay, so we should end up with 30 here, 30 ATPs for 2 pyruvates that we start with. Could also ask you how many of those are made by chemiosmosis. Well, all of them are going to be made by chemiosmosis except for these 2 right here. So 28 by chemiosmosis. Okay, 2 by substrate level phosphorylation. Okay, so do some of the practice questions to make sure that you can calculate yields starting at places other than actually glucose, and also to make sure that you understand which ATPs are made by chemiosmosis and which ATPs are made by substrate level phosphorylation. Okay, now that we've talked about the whole process of cellular respiration, if we just talk a little bit more about why we have an inexact number of ATPs. We've been saying a maximum of 38 ATPs, and we've talked about one reason why it varies a little bit. But there are several reasons. First off, the phosphorylation and the redox reactions are not directly coupled to each other. What this means is that the NADHs may be passing their electrons in one location, and the ATP synthase is working in another location. So when those hydrogen ions are pumped across the membrane by the electron transport chain, they don't turn around and flow immediately right through the ATP synthase. This creates more of a range of ATPs that we get for NADH. It's really more like 2.5 to 3.3 ATPs. We're using 3 ATPs each as a nice even number. Of course, depending on which end you were at, if you were at 2.5 versus 3.3, you'd get a different overall number for your NADH ATPs. We did show the shuttle varying when we transport the electrons that were collected in glycolysis into the mitochondria. Depending on how we get those electrons from NADH into the mitochondria, we will have a final number that is different. And then lastly, this proton motive force, or this hydrogen ion gradient, is a valuable source of energy. That source of energy may be used for work other than actually making ATP. So if, for instance, we had some other molecules that needed to be moved across the membrane by active transport, we could use co-transport with the hydrogen ions to make that happen. So keep in mind that every hydrogen that is pumped across is not necessarily going to return to the matrix through the ATP synthase. It may return through a different mechanism.